Hi everyone, welcome to the last talk of today, and my name is Nora, and I'm a PhD student currently at MIT. Today I'm going to talk about this work titled Scalable Surface Code Decoders with Parallelization in Time. So this is a joint work with Fan, Ray, Yaoyun, and Jianxin when I was interning at Alibaba Demo Quantum Lab 2 summers ago, 1 summer ago. All right. Also, the credits of those slides go to Ray, and who generously allowed me to borrow them for the talk today. Okay, so I want to motivate this talk from a slightly broader perspective, that is to understand the role played by classical processing for quantum fault tolerance. And a natural question to ask is classical processing really necessary for quantum fault tolerance? So this question was answered in one of the first paper about threshold theorem. In 1999, this seminal work by Aharonov and Benor, they said that no measurements or classical operations are required during the quantum computation. So it says that you can have quantum fault tolerance without using any mid-circuit measurements. So this is good news in theory, because it means that the quantum model is complete. We don't need, it can be made fault tolerance by itself without any help from the classical operations. However, in reality, having classical processing would be useful because we care about not only having positive threshold, but also a large threshold. And we want to minimize the space-time overhead as much as possible rather than just having some poly or polylog asymptotically analysis.
Let me just say that just prove that there's a threshold. We never compute it.
Okay, yeah. Okay. Here, let's go back to classical processing. It's a little bit hard to list everything that you do in classical operation. Here are some examples. So post-selection is based on error detection, and it's being used in the ancillary verification procedure and also in magic state distillation. And physical level feed-forward is also very general, meaning that I want to adaptively determine a subsequent syndrome extraction circuit based on some previous poly measurements. And the third decoding part, I'm referring mostly to the non-adaptive part of your error correction protocol. For example, the well-known minimally perfect matching, unified decoder. So the outcome of your decoding algorithms are poly operators. But you will never need to physically apply them because you can just keep track of them. So that's why we say it is non-adaptive. Actually, yeah. And the last point is logical level feed-forward, and is used in logical gate teleportation. And today's talk, I want to focus on the last two classical operations here, and the dependency between these two and the interplay will result in an issue called exponential backlog. So this is proposed by Terho in a 2013 review paper, and our result just mainly focusing resolving this issue. So let me start with a brief recap of what gate teleportation is doing. So our goal here is we want to implement this logical T-gate, and we have a data block, we have our magic state, and we do this logical poly-Z measurement, and you have a classically controlled phase gate. So you maybe wonder, because this phase gate is a Clifford gate, so Clifford frame is also can be made adaptive, non-adaptive as the poly frame. So why can't we kind of keep track of the poly frame and make it non-adaptive? It's to avoid the logical feed-forward. However, this is true if you are implementing a single logical T, but things are different if you want to have multiple non-Clifford operations. For example, I want to implement this THT. So what I do here, very simple. I copy-paste these two gadgets, and I apply a logical H on the data block. And an equivalent way of seeing this is that we merge this S, H, and C naught together. So we will have a logical Clifford frame. exactly as what we want. So if and what it looked like will be controlled by this B, the measurement result from this gadget. But the catch here is we cannot carry this logical Clifford frame one step further to the next measurement, because this is another equivalent way to think about this is this P will be a adaptive logical poly measurement. So dependent on the previous measurement results, you will be measuring something in two different bases. So that's why you have a unavoidable logical feed forward. And if we look at the setting in a more general case, and we want to apply in the sense that we want to apply this TH for n times, and we will have a lot of logical poly measurements sequentially, and each one is dependent on the previous measurement results. So P2 will be dependent on B1, and P3 will be dependent on B2. So on and so forth. And because we want our entire procedure to be fault tolerant, we need to apply quantum error correction constantly. And this means that there will be syndromes generating all the time, idling or during P1 is measured. So the time to determine B1 is only after we obtain and process all the syndromes of P1, PI, yeah, BI and PI. And it will be useful to define two speeds. The first one is the rate of processing, and this is the classical speed, the number of syndromes that classically you can process per second, and the second is the number of syndromes that your hardware can be generated per second. And it will be useful to also to figure out what is going on with the time. And we define the time when B1 is determined called Ti. Bi is different than Ti. So here, starting at 0, and when B1 is determined, this is T1. And when B2 is determined, this is T2. And as long as we said, once Bi is determined, we can start to measure the next Bi, because the basis will be determined. And then we will have two inequality, two bounds. The number of syndromes, let's take this B2 as an example. The number of syndromes required to determine B2 will be lower bounded by Rgen times T1. And this is simply because this interval is smaller than T1. And by definition, this will also be bounded by the rate to process those syndromes times T2. And you can generalize this to I. So Rgen times Ti minus 1 smaller than R produce a process times Ti. And that's where you have the exponential backlog. So your time in your entire procedure will just grow exponentially if your processing speed cannot catch up with your generating side. So this is bad, obviously. Okay, so I just give you a very toy model of where this problem would occur, but it's actually everywhere in teleportation-based protocols. I won't go to any of them in details. And it also seems pretty common for any universality approach based on teleportation. And by teleportation, I mean that you want to implement a logical non-Clifford operations using logical magic state and logical Clifford operations. And this exponential backlog will always be there. If your speed don't catch up. And in our paper, we focus on topological codes. Yeah, so like universality-based teleportation occurs in all these codes scenario, and we focus in this paper, we focus on topological codes because it's like the well-studied codes and it's simple to formulate, and it's syndrome extraction circuit. The decoding part doesn't involve any post-selection or physical level feed forward. And what we propose is a scheme, decoding scheme that can address this backlog problem. As I said, here is a very general picture of what the decoding scheme look like. So the time goes from left to right. And here we have a 3D decoder graph of our code. Because we're like considering a surface code, so you imagine the space is in that direction. And we have some red defects that the observed thing. These are essentially our also input to the program. What we do is to divide the entire decoder graph into 3 blue areas, and you also extend them into some buffer regions. And the catch is each of this block, subgraph, can be handled in parallel, and there will be a way to merge the results back together. So the decoding throughput, which is also the number of syndromes you can process per second, defined by this R process, will be proportion to your level of parallelization, and it will be independent of RGen. And in the end, our protocol scheme will have a constant overhead instead of having this exponential backlog. Yeah, so another thing about fault tolerance is we also care about accuracy. In addition to having a fast processing speed. So we did numerical simulations saying that if you properly choose your buffer size, then your memory experiment, the logical array, will be almost the same as you do offline decoding. And by offline here, I mean you just wait until everything is over and you take everything into your decoders. So this is essentially the best thing you can do if you fix an inner decoding algorithm. Some related work, our work was inspired by this overlapping recovery proposed by the seminal work Dennis et al. In 2001. This was also recently rediscovered by Das et al. In 2021. In a sense that they also divide the entire 3D decoder graph into windows, and they are overlapping in the buffer region. However, a key difference is that their windows are sequential, saying that the second window will be dependent on the decoding result of the first window. However, in our procedure, they're all independent. That's why you have this parallelization, and you can just arrange them to a lot of classifying units to go through. Another related work, this parallel window decoding by Sarek et al. This paper was posted to arXiv on the same day as ours, and their results are, I would say, essentially very similar to ours, essentially the same to ours. Yeah, okay. So another recap of doing error correction with topological codes. It has deterministic syndrome extraction circuit, and it periodically generates 0-1 outcome of the poly measurements. So in our paper, we just go with rotated surface code. But for this talk, because repetition code should be something that everyone knows about, and it's very simple to describe and display, so I'll just go with this repetition code. And in this little demo, we are trying to preserve this logical 0 state with a distance 4 repetition code. And we perform 4 cycles of syndrome extraction. So 1, 2, 3, 4. And each time, so we have 4 data qubits, 1, 2, 3, 4. And we have 3 ancillary qubits. Each time there will be 3 measurements. So 1, 2, 3. And in the end, we just measure each of the qubits in the Z basis. Z basis. Oh, and the task of this, the goal of this memory experiment is we don't want to introduce logical X error. And the logical X operator will be transversal X acting on each data qubit. And our goal is to not letting that happen. An important idea is we define something called detectors. It has many other names in other literature, but we'll just stay with detectors in this work. They are the XOR of outcomes in different, so adjacent times. So essentially you take the XOR of this column with this column, these two columns, adjacent two columns. So you're like learning something happening in time. For example, this will be a detector. You can take the XOR of these two results. And the detector will always be 0 in the absence of error. And then we can form our decoder graph. Each vertex will be associated to a detector. So these two outcomes, XOR, will correspond to this vertex. And this outcome will correspond to this vertex. And the XOR of these three outcomes will correspond to this vertex. And if there is, if something is red, meaning that the value here is a 1, we call it a defect. This means that something is wrong. I need to figure out why, where. An example is an X error before this measurement, it will flip the result. And by flipping, if there's no error elsewhere, this is 0, and this is 1, this is 0, and this will cause 2 defects in the decoder graph. So if you match them, you can see, oh, here's an error. And an important observation is that the detectors flipped by an elementary fault are geometrically local. And by elementary, I'm referring to the stochastic polynoise just attached to each of the elementary operation. And because they're local, we will have a very nice looking decoder graph. So actually, this is a complete decoder graph of what is going on here on every level of this repetition code circuit. And we will associate the edge with faults. So for example, this fault, like I said, it will flip these two vertices. So we'll just assign an edge to the edge set, indicating it corresponds to this. And for here, if there's an error here, it will flip this one vertex only. So this is actually a unary edge in the sense that the entire thing is a hypergraph, which makes sense. And another example here, if an X, you'll flip this edge. Different faults may flip the same edge. Just to like an example, trivial example, see it, if you have a Y error here, it will obviously also flip the same edge. So you can keep track of your probability of errors happening associated with these edges. So the decoding problem, to summarize it, is we have some underlying ground truths that is unknown. They are the faults. There are some edges, and we will observe defects because of these faults. And the goal is to find corrections, which are also edges, which are your guesses of the location of faults, such that they satisfy D. But there are also many ways to describe this satisfaction, like annihilate the defects or like some error assignment. But here I'll just keep using this satisfy because it's the shortest and throughout the talk. So whenever I say some corrections satisfy D, it means the same thing as these corrections annihilate the defects. And a goal is the corrections, so together, the correction and the faults, they should have non-trivial syndromes or defects. They should have trivial syndromes or defects. Not only that, so a valid correction means that you collectively K plus D, K plus F, you have no defects. But to say that you successfully preserve the state, you must maintain the correct logical polyphrase. saying that in the end, it is still a logical 0 state, but not a logical 1. So we are worried about having the logical X happening. And yeah, so you want to make sure that it doesn't happen. Or in our memory experiments, how you keep track of whether such thing happens is, this is like operational sense. You can like find a cut because X is only happening vertically. So you can just keep track, find a cut and count how many times your correction and faults have came across it. So if it come across it an even number of times, then you're okay. But if an odd number of times happening, then you just revert your state. So now we can look at more cycles of the repetition codes. And we call this sandwich decoding, by the way. I forgot to mention that. I didn't put any defects in the graph. So you can imagine there are some defects there. So the first thing is we partition everything into colors. So we start with the vertices. There are blue vertices and green vertices. We also partition the edges. There are blue edges, yellow edges, and green edges. And yellow edges are the ones that connect the blue and the green. So the defects will also have colors. And when sandwich decoding will have 2 stages. The first stage is we don't care about the things going on at the green vertex. We also don't care about whether they're satisfied or not. So we only want to find corrections, meaning the blue edges and yellow edges, such that the blue vertices are all satisfied. So we just satisfy all the blue vertex in the first stage. And of course, there will be something not happy with the green vertices, and that's what the second stage is doing. So the second stage will focus only on the green area and find things that make the green areas happy. So collectively, it gives a valid solution. And because those blue patches are disjoint from each other, so you only need to look at this region that you cut it from here. You only need to look at these 4 columns to find a valid solution. And for the middle part, you only need to look at these 5 columns to find solution. And the last one, you only need to look at these 4 columns to find solutions. This is where the parallelization comes in. However, if you only do that, like what I described, you just brute forcefully cut it from here, then your results are not accurate because you may have faults that come along from this direction. Like it could be something crossing, but you're cutting it here, so your decoder doesn't know what's going on in the future, or your decoder doesn't know what's going on in the past, and it may miss a sign. So that's why we need to have buffers. And the buffers, so we all have this core region and buffer region. The inner decoder will work on the core and buffer together, and it will also be able to read what's going on in the buffer, like the defects information, but it will only assign corrections and retain corrections, most importantly, on the blue and yellow edges. And similarly, for this middle layer, it will read. So imagine this procedure, syndrome extraction, is like infinitely long. So this will be a relatively small window. The core will be able to understand what's going on in the past, like a proximate past and a proximate future, but it will only retain the information, the reliable corrections in the core. So, and everything generated in the buffers will be discarded. And then, because we have figured out all the blue and yellow already, we need to, the only dependent components to this green areas are like all done. So we're able to figure out the corrections in the greens. And we don't need any buffer for this area because we trust, due to the buffer in the first stage, we trust that these yellow edges have been reliably handled. And similarly, we will have a last window here. It's also the first stage, and you can handle something between the second window and third window. Similarly. So that's what's going on with sandwich decoding. Very simple and straightforward. And it has a lot of flexibility as well. For example, you don't really need to only work with repetition code. Like there are many codes that you can choose from. And for, like I said, when you are decoding each window, there are many choices of an inner decoder that you can use. You're not binded to use only minimum perfect matching or unifying. And how you select the partitions are also very, there's also a lot of freedom in choosing the partitions. So we actually tested among many different choices, and they're all, can't tell which one is good or bad. So if we move on to surface code, the 3D decoder graph, you partition it into, partition I'm referring to the dark shaded blue region, and extend it by a buffer. So the blues are destroying from each other, but the buffers, they overlap. And they will result in this green layer being not handled in the first stage. So the second stage will be handling what's going on in the green region. And we perform circuit level simulation for this memory experiment with depolarizing noise. And we choose our window to be T cycles buffer, T core, T buffer again, like this sandwich shape for B, B. And we respectively perform minimum perfect matching and unifying as an inner decoder. And we calculate the logical error rate per D cycle and figure that you almost get the same performance as offline decoding. And you almost have the same threshold, like slightly smaller threshold compared with the offline decoding. So this means that you don't lose anything by this parallelization if you properly choose the buffer. So a summary, we propose this decoding scheme, sandwich decoding, for topological codes. And we say that this is like a parallelization in time. But also in reality, it's okay to, it's possible to also parallelize in space. So you can do that similar thing in lattice surgery. And the decoding throughput, in this case, will be proportional to the level of parallelization, and it is independent of your generation speed. And that's how you resolve the backlog issue that occurred in teleportation-based universality. And we showed that you can maintain the accuracy of offline decoding by adding buffers. For some possible directions, it's worth studying the decoding throughput for concatenated codes and LDPC codes, because that's something we didn't look at in our paper. And it's also worth looking at the feed-forward for universality involving physical non-Clifford gates. Here are some choices. And I want to end with some other interesting related later works that I find in some extent related. The first is modular decoding. They did something very similar, but they also added some proof, theory discussion in their paper. And this fusion blossom, they implement a fast memory perfect matching with a parallel implementation. And if you're not doing it in parallel, their algorithm is almost linear in the number of defects. And then they implement it in a parallel fashion so that it can be adapted to the real-time decoding scenario. And the sliding window decoding for LDPC codes is, I think, also very interesting. It's very recent. They shows that for LDPC codes, even though some of them are able to do single shot, but sliding window decoding can significantly improve the logical memory lifetime and hence the effective distance. And this improvement may not cause a larger decoding complexity. Their paper didn't implement this in a parallel fashion, but I think the idea of using sliding window for LDPC codes is already pretty interesting. So with that, that's all for my presentation today.
Thank you, Noah. So if I was to sort of try this out, so let me tell you sort of the story. So I have a stream of syndromes, and basically I separated in the slices of T lengths. And first I have a blue region of length 3, T, which sort of, but then when I decode it in that region, I ignore all the other parts of the graph, all the other errors, and I retain only the errors in the middle block.
Yes.
Okay. And then I do it for every blue region. But then how do I reconcile the results? You are saying this is what the green region is for. But question is, how do I guarantee that I really get the minimum global solution when I'm doing the reconciling? Because when I do, presumably some line connections will not work as they should.
Yeah, so this is like a theory question. Like, for example, if we choose minimum perfect matching, you're saying, oh, it's not guaranteed that the merged solution is globally min-weight. That is true. And I don't have an answer for that because I've actually tried some months trying to prove that by properly adding buffers and dividing the windows, you can generate a high weight or a low weight close to the global minimum with like high probability, say. But I failed. I didn't have anything. I guess what can be think of optimistic is that the logical error rates are indeed close to what it looked like in offline decoding. And the threshold are also close.
Okay. So now, do you actually need the blue region? I mean, in reality, are there a lot of errors that come into the green region where you have to do the reconciliation? If you take your buffer zones big enough, don't you expect that all errors will sort of end doing true minimum weight decoding?
Are you saying why can't we just do offline?
Well, no, I'm saying if you take big enough T, I generally expect that sort of the results in the middle to be correct.
Yes.
Okay, and you probably do. And then, but then you probably don't need the reconciliation, no? Why do
I think there's still possibility that they are not valid solution in the sense that they cannot annihilate the second stage. So, and we also did experiments on making the green area bigger. So we actually did 3 kind of overlapping scenarios. So you have a positive offset, you have a 0 offset, which is what you see here, the 1 layer green thing, and you also have negative offset. We wanted to know which one is like better, and it turns out that you can't really say which one is better, as far as based on the numerics that we did. And in theory, I also don't know which one should be better. Yeah.
When you make the thing smaller, like, did you see how small it can be before you get a bad accuracy? Like, is a D the distance, or how small?
That's really like a numerics. Yeah, like apparently if you get too small, then it's not reliable. Yeah, one slice is definitely not reliable. So that's why we don't want it to be too small and we don't want it to be too big, because if it's too big, then what's your advantage? So we picked this D plus 1/2, so like half. And that sounds like looks like a sound thing to do. Are you okay with this?
Yeah, I'm okay. But
Okay.
I didn't know if you could go like even smaller.
Maybe that's a good question, but if you just cut divide by the region without introducing any buffer, and then instead of considering buffer, just put boundary edge boundary vertex, this may match.
One thing, so
Does this work? Or apparently this impacts the threshold, but my question is, this still works or this doesn't work at all?
so first of all, just to clarify, I don't think in reality is D by D by D, because in reality you want to have gate teleportation and you will have Clifford operations between your consecutive non-Clifford. So that can be arbitrarily long.
Yes, it's wrong.
Yeah.
What I'm saying is just divide it by D.
Oh, D by D by D. Yeah, in that case, oh, yeah, without overlap, without buffer.
Just without introducing buffer, just add single.
No, you need buffer. So we also numerically found that you need, as the buffer increases, you will have your subgraph can see more info compared. So it will generate something closer intuitively. It will generate something closer to the global mean weight, right? And if your buffer is entire thing, like a trivial buffer, then you have global decoding, and that global is the best that you can do. Does it make sense?
Yeah.
Yes.
Can the decoding also be made such that X and Z decoding is correlated?
That's a very general question.
Sorry, like so it sounds like the procedure right now is that X and Z graphs are separated, right? And you just run
Yes.
them. So then is it easy also to incorporate a noise model such that they can be linked together simultaneously with this parallelization procedure, or is it really treated as separate?
Yeah, so what we consider here mean weight perfect matching and unified, they're heuristic algorithms. So if you're considering like taking the noise more appropriately, then you may be considering like maximum likelihood. That will take into the coherent noises into account, I think. But here, they're indeed, like you said, treated separately.
Oh, okay. I guess it's like a pedagogical example is let's say you always get Ys, right? Then you would expect kind of on the graphs they would line up. So I guess I'm just asking, like, is that easy to connect those points and parallelize simultaneously?
I'm not sure I understand,
Maybe we
but I think, yeah.
Sort of to follow up the same question, so you don't really care what kind of decoder you use for each sort of stage. If you have minimum weight perfect matching, that would be one decoder, but you could have BP plus OSD, for example, and use the same algorithm in separation. In general, you expect it for, I mean, there may be some differences for the codes, but in general, it should just work, right?
I would say most decoders will work, but indeed there are some cases that doesn't make sense. Like if you consider those cosets, then because your window, it's hard to define what are the cosets, like maximum likelihood, because you're then you cannot do this kind of window thing. So for minimum perfect matching, there is a good understanding of what you are doing, like what your the corrections. They are the minimum weight based on what you see, so they can be merged.
But in the class of minimum weight decoders, it doesn't appear to be much difference.
We've never tested it, but naively you can do a mixed minimum weight and unified. I'm sure that will be fine.
I'm curious if we could solve the backlog problem without decoders, just by designing a universal gate set for which we don't have a backlog problem. Do you think it's possible?
Do I think it's possible?
From state injection, right? So if I do it in a different
Yeah. It's definitely possible if every classical thing that we do is fast enough. So you can just avoid it from the very beginning.
Mm-hmm.
So, but the case is we don't have, and our hardware is too fast. But also, according to what John said, you don't want it to be fast. You don't want it to be slow. You want it to be you want it to keep it fast. So that's a hard problem.
More question?
Is it easy to like explain that how the technique in Future Blossom is different, or is it very similar? Either one you mentioned.
Yeah. So based on what I know, Fusion Blossom, they use something specific and they modify the Blossom algorithm. And they use this parity Blossom or sparse Blossom by another independent work, such that it's very specific to the Blossom algorithm that it can be made parallel. So yeah,
I see.
it's very different from the nature of this work. And I've tried sometime trying to prove that you can approximate a globally min-way solution until I read about US paper who showed that you can do exact min-way perfect matching. You got an exact global min-way solution using this parallel fashion. And I just gave up on that problem. Yeah.
Great. Let's thank you. That's the end of the day, and where is